Okay. Good morning, everybody. Welcome back to Control Systems 1. Please take a seat. Okie dokie. Are we good to go? Hey, coming in now. Anyways, ready or not, here we come. So, what's going on in this course? Last week, we talked a little bit more about systems. We understood that in control systems, as the name might suggest, the world, the cosmos, excuse me, take a seat, is seen as a number of interconnected blocks that have inputs and output signals. This is a convenient representation. It makes our life easy because it helps us break down all the problems we understand. And we started seeing how different systems, if they interconnect with each other in different ways, in series, in parallel, and feedback, they can be represented as other systems. We described what a system is, what kind of properties it might have, and we reduced the scope of what we're going to look at in this course to linear time invariant systems that are single input and single output. So after having pretty much put a boundary around what is it that we want to study, which are these kind of systems that might be look like a very small subset of everything that is out there, but still they are relevant because they are, first because the math is easy, and we'll see that we'll be able to do lots of things with them. We'll be able to study these linear time invariant systems in detail, and that's always good because we gain insight. And then we see that although most of the systems of the out there are nonlinear, linear time invariant systems, work as good approximations in around specific points. We moved forward to then try to express this linear time invariant system with some kind of general mathematical formulation. And to do so, we had to first introduce this concept of state variable or state variables. And we described a state variable as something, a quantity that keeps track of everything that has been going on since the beginning of time in minus infinity, up to some time t0, such that the output at a time t1 bigger than t0 can always be expressed as a function of that state variable at time t0 plus the knowledge of the input, of course, between the time t0 and t1. This is because we looked at the fact that the systems we study are causal systems. This means that they are the output at the current time instant is affected only by the history of the input, so the input from minus infinity till the current time. But that's a lot of stuff to remember, so we introduced these state variables as a way to keep track of introducing a memory variable in the system, so that we can forget what happened from the minus infinity of time and just focus on the single variable. Now, these state variables allowed us to really? Here we go. So state variables allowed us to write any linear time invariant system with this formulation. This is a very important formulation. You might want to make so that you remember it if you're waking up in the middle of the night. And basically, remember always that in this course, we're talking about single input, single output system. This means the inputs are just a 1-by-1 single input, and the outputs are a 1-by-1 because it's a single output. So this means that the state variables, which are typically a collection of n quantities, mean that the other matrices in here have dimensions. If x is an n-by-1 and s is an n-by-1, then A must be an n-by-n and b must be an n-by-1. Similarly, u is a 1-by-1, y is a 1-by-1, x is an n by 1, this means that C must be a 1 by n, and D must be a 1 by 1. Depending on what kind of system we're studying, so what's the physics that goes on in the background, X can be a bigger or smaller collection of variables, and n is what we will call the dimension of a system. So this was nice, and but we got to the point where we said, okay, but so linear time invariant systems are beautiful, but they're only meaningful as an approximation of a nonlinear system. And we were trying to understand, so how do we go about actually linearizing a nonlinear system? When is this approximation meaningful? Where and how much? So always keeping the notation of inputs as u's, y's as outputs, and x as state variables, we can write nonlinear systems with this general representation here, which basically says the evolution of the state variables is whatever, is an f function of the x and the u. It can be any arbitrary complicated function. And so is the output is some function g of x and u. Keep in mind that maybe it's worth stressing that we see the world as inputs going in some system. We call them sigma at the beginning. So this would be the sigma system. And y is the output. So u is something, always think about it as something we can control, we can modify. The user gets to decide what u is, okay? Y is the only thing you get to know from the system. Y is what you can measure, it's the output, it's whatever comes out of it, okay? Anything else is not available to us. So the state variables, which kind of encode the whole deal going on, the whole dynamics of the system is expressed by x dot equals something as a function of x. X is not available to us, okay? You can't measure x. So going forward, keep in mind that y, you measure it, you know it. U, you decide what it is. X, it's just the dynamics of the system. It's what goes on in the background. Okay, so we got to this point, I believe, last week, where we were looking at a nonlinear system. And we wrote the equations of equilibrium of this pendulum by simply doing the equilibrium of torques around this point here. And we got this expression. Now, it's relatively relevant how the expression is derived. What matters is once you have an ordinary differential equation that describes the behavior of some system, we can always transform it in this representation with state variables. So how do you do it? Typically, you have to identify one variable that kind of represents an energy reservoir or something, this variable that the state variable, which keeps track of what is going on. Here it is, in this problem, it is intuitive to select as first a state variable the angle. It is the position of the pendulum, because that, of course, takes into account what has been going on before. And you will notice that the equations of motion here are characterized by a second-order differential equation. This means that we will need the two state variables, so we define the second one as the derivative of the first one. Here you will see that x2 is equal to x1 dot, which is theta dot. And therefore, we can rewrite the equations of motion in this way. So in this case, before we wrote x dot is equal to f of xu. So here, please just forgive me the fact that I will not rewrite every time the dependency on time, okay? I'll just drop it, but it's intended that x, u are all functions of time, unless it's specified otherwise. So x dot is an f of xu, and what is f here, right? So what is x? Because here on one side we said x, on the other side we said x1, x2, xn, how many x's depends on the problem. So x is always, as we said, a vector of Rn, right? So it means in this case, x is defined as the stacking up of x1 and x2, okay? And what is f? In this case, f is these two equations. So f itself has two components, has an f1 and f2, no? So we've got x dot, and if we want to rewrite the problem like this, we would have x1, x2 dot, both are derivatives, derived in time, is equal to what? The first f, this would be f1, of xu. And the other equation would be this big mess here that we just put in here. And what is the output? Well, the output, somebody asked last time, is whatever we want to measure, right? We could choose to measure the position. We could choose to measure the speed, the angular speed, of course, the theta dot. We could choose to measure any y that is a cx, but c, it's a vector, right? So it's, what does it mean? A vector has a bunch of numbers inside, and you have a 1 by n vector that multiplies an m by 1 thing. All you're doing is just doing a weighted average of the x vector, right? So especially when we studied linear system, you can always think as the output as a weighted average, not an average, a weighted sum of the state variables. So, okay. Now, the next step. Now, linear time invariant systems, when are they good approximations of nonlinear systems? So again, I would like to stress the fact that linear time invariant is a subset of something very specific, very well determined. Nonlinear is everything else, okay? So it's difficult to say general things about nonlinear systems. You always have to specify and say, okay, give me whatever nonlinear system we're studying and we'll tell you what's going on. But, so, there is regardless of the complexity of the nonlinear system, there's always going to be points, special points, where the dynamics kind of settles down for a second, okay? And we call those points equilibrium points that are defined such that the x dot is equal to 0 at that point, fundamentally. And a point here is to be intended as a combination of x and u, okay? So an equilibrium point is a combination of equilibrium states and equilibrium input. Remember that this could be actually x1e, x2e, and so on, right, up to xne, because they're n state variables. Such that, what happens? Such that x dot, which is equal to f of xu, when evaluated in xu equal the equilibrium points, it's equal to 0, okay? As a consequence, we've defined the equilibrium output, y, as the g of the equilibrium points, and the equilibriums of points are just calculated from the previous step of setting to 0 the dynamics. Okay, so what's the equilibrium point for a pendulum, right? So this is just a straightforward math. So how do we do it? We do it by setting equal to 0 the f of xu. In this case, the f of xu, as we said, is these two equations. So what we do is we set them both to 0 and find what are the combinations of x's and u's that satisfy those equations. So from the first one here, it's obvious that x2 is equal to 0. Then we just plug it in the second one. This goes away. It means we have minus gl over L sen of x1 plus u equal to 0. Now, we're considering linear time invariant systems. So it means that u and x, the equilibrium points, are constants, okay? So the only way the sum of these two terms is going to be equal to 0 is that each one of them is equal to 0 if u is a constant, because it can't just be equal to the opposite of minus g over L times sine of x1. So we'll say that u equilibrium is equal to 0. This goes away, and then we have to say when is this term equal to 0. So I always get confused. We do a little bit of trigonometric circumference. X is this one. The signs are here. When are the signs equal to 0? When the x is x1 is equal to 0 plus an integer time of jumps, of pi jumps, right? So we can just, we're studying a physical situation. It's a pendulum, so if you just flip over how many times you want, you basically always end up in the same position. So really what we see from here is that there are two equilibrium positions, actually. Note, the equilibrium point, nobody said it has to be one, right? It could be how many you want equilibrium points. So in this case, the two equilibrium points is called x1 equilibrium A, I don't know, is equal to 0. And x1 equilibrium B is equal to what? Is equal to pi, okay? So we got two equilibrium points, which are represented here. One is x0, 0, where x1 is 0, x2 is 0, and u is equal to 0. And the other one has pi there. Are there any questions, comments, or doubt on this? Speak now or forever hold your peace. Yes. Okay, so very well. We found the equilibrium points. So what does the equilibrium point mean physically, intuitively? It means like all this mess of a nonlinear dynamics going on. If you choose that sweet spot of inputs and states, then the system will actually stay there, okay? If you pick as an initial condition the equilibrium state, and you apply the equilibrium input, nothing will happen, because x dot is equal to 0. The dynamics will not change, right? So, okay, now that we've got these special points, which mean that they're special because things don't change too quickly around them, then those are the ideal candidates where we can approximate the local dynamics with a linear time invariant system, and the approximation is going to be representative. It's going to be a good approximation. So how do we actually derive now the ABCD matrices from this FG random nonlinear things? Well, what the idea is that you substitute x, u's, and y's in the nonlinear system with the equilibrium point plus a perturbation, okay? So imagine this being time. This is not a rigorous thing, but it's just to give you an idea. And this is x, okay? So it's like how the state variables change in time. A nonlinear system might be something that goes very changes very non-linearly. And what we're doing is we're selecting an equilibrium point, like for example here, but it could be here, it could be here, it could be any other point that has x dot equal to 0, a tangent equal to 0. And we're saying, look, what we're doing is we are approximating the dynamics of this nonlinear thing in some neighborhood of the equilibrium point as a linear system, right? So how do we get the equations of motion in that case? Well, plug in the actual equilibrium point that we derived from the passage before, plus a perturbation. Okay, a perturbation is what is represented by these delta x, u's, and y's. So the perturbation means I'm moving around here of some delta x. Okay, now x basically, let me go back to blue. Delta x is basically x of t minus the equilibrium point. And similarly is u and y. So, well, this being things defined in this way, this means that if you take the derivative of delta x dot, well, x is a constant, so you get x dot, and so holds for all the other ones. And the idea is that these perturbations have to be small, okay? Small, what does it mean? Depends, right? So the idea is the smaller it is, the more the linear approximation is correct. It's a good representation of the dynamics. So, okay, let's do it for the pendulum example. We plug in, first we start from the 0, 0, 0, the first equilibrium point. If we plug in the values, we see that what we get are these equations here. So this was x2, so we plugged in x2. Instead of x2, we plugged in x2 equilibrium plus delta x2, and we did the same thing for the other variables. Here, if you notice, we had a sine of x1 that became, so it became the sine of x1 equilibrium plus delta x1. This was equal to 0, so it went away. And we said that delta x1 is too small, right? So a sine of a small angle can be confused with the angle itself. It's an approximation. And so what we get are these equations here. So basically, if it works best for you, you can imagine the perturbation variable to be a different variable. Just redefine it as z, okay? And delta y can be, and delta u can be, I don't know, a v, and delta y can be, call it as you wish, w or something like that. So in this case, this just becomes z dot is equal to az plus bv, and w is equal to cz plus du, which is a linear time invariant system, okay? And the a, b, c, and d matrices are these, are directly buildable by inspection of the above equations. So you'll see, if you just stack these up, you get delta x1, delta x2 dot are equal to what times delta x1, delta x2. If you look at the equations, delta x1 is just a function of delta x2, right? So it means there's a 0 here because delta x1 doesn't show up in the equation. And then there's a 1 here. And for the other equation, delta x2 dot is equal to what? Well, there is a minus G here over L that multiplies X delta X1. And where is it? There's a minus C over ML squared that multiplies the delta X2. Okay? And in this way, you can obtain a representation of the linear time invariant system that approximates the nonlinear one. Now, this we did it for the first of the two equilibrium points. Then there is another one, and we could just repeat the whole process, and we would see that what really changes is just this sign here. And now it might not make much sense to you guys, but we'll see how it is fundamentally a critical piece of information that we will understand how to interpret by the end of this lesson, if we get through it. So this is an equivalent approach. I won't go into the details of this. I just want you to have it as a reference. It's actually the one I prefer in the sense it's more systematic. You just do the calculations and you can make it always work. All you're doing basically is taking the nonlinear system, you calculate the equilibrium points, step one, you plug in the equilibrium points, and you just do a Taylor expansion around the equilibrium point of the nonlinear functions, right? So a Taylor expansion of x dot is always going to be the function evaluated at that point, plus a first order term, a second order term, and so on, right? So hot here means higher order terms, which are neglected, of course, because it's a linear for representation, first order. And basically, what you do is you say, well, a function, any function can be always approximated as the evaluation of a function at a specific point, plus the first derivative, plus the second derivative, with some coefficients in front of it. So here, really, what we care about is just the first terms. And f of x at the equilibrium point is equal to 0 by definition of equilibrium point. That's how we calculated them. So this part goes away. And what you're left with is this term here, which is basically the partial derivative of the various components of f. We saw before, even for the simple example of the pendulum, f was an f1 of x and f2 of xu. So in this case, A would be a matrix that represents an m by n matrix. Remember, that's like a constant, where the first component would be the evaluation of the first component of f by the first state variable. And then there would be, imagine it here as multiplied by x1, x2, up to xn, right? So every partial derivative has to match with its proper x2 with its proper state variable. Here, the second component would be df1 over dx2, and so on up to df1 over dxn, and you can fill the whole matrix, right? And the same goes with the B matrix that can be expressed like this. So this is a nice way to calculate the A, B, C, D matrices without doing the perturbation approach, but it's basically the same thing. So this was just a recap of last time to wrap up the class. So what are we going to do today? Hopefully I've convinced you that linear time invariant systems are meaningful, somehow, useful, worth spending our time on. But how do you solve them? Right now we said, look, we understood physically what we want to study. We understood mathematically how to write it down. Okay, but what's the solution, right? So we have x dot equals ax plus bu. So it's a differential equation, so you must have initial conditions, otherwise you don't go anywhere. So given initial conditions, given an input signal, so given an initial condition at a certain time t0, t0, and given us an input signal from t0 to the current time t, and given the knowledge of the system, or at least the model of the system, which is the matrices A, B, C, and D, what's y of t? What's the output? What's the state? What's x? How do we solve it, right? So that's what we're going to do today. And then you might recall the first class, we mentioned at some point, we said, okay, so why are we even bothering to study control systems? What is the main objectives of control systems, right? And we said, first and foremost, you want a system not to blow up. It has to be stable, okay? Because otherwise it breaks down. Second, you want the system to be performant. So it means not only it won't blow up, it will do what the user wants it to do, and it will do it in a timely fashion, in a proper fashion. And proper is according to the specifications that the engineer just throw at it, right? And then it has to be robust. And robust is something that we'll deal with later on. Robustness is the idea that a control system that is designed to work on a nominal system actually works more or less, even if the system is not exactly as we thought it would be, okay? But that's not something we will treat in this course. So today we will study what does it mean to be stable, okay? What is stability and how do we how do we know if a system, a linear time invariant system? So from now on, we're just talking about linear time invariant systems unless we specify otherwise. How do we tell if it's stable or not in an easy way? So what are we gonna go through today? We're gonna see the responses of linear time invariant systems, some mathematical tricks we need to know to figure things out, and we'll define stability and hopefully see by how to figure out if a system is stable just by looking at it or doing some minimal calculations. Okay, so let's start with this example. Remember, now the objective, what we're doing from now on, is to get to an expression and an understanding of the x dot equals ax plus bu and y equals the cx plus du equations. Okay, we want to express x of t is equal to something, y of t is equal to something. Okay, so imagine it's deep winter and you're returning to your cabin in the middle of the woods. Okay, why would someone want to go in the cabin in the woods in winter? This is a different question, not our topic of discourse. So let's say that before you leave the cabin, infinite time ago, we left the heater on, and outside the temperature is very low. Okay, so in this graph, we have a U signal, which is the input. The heater is set as some input 1, whatever that means. And the outside temperature, as we said, is the outside temperature is 0. So this is 0, and it's the outside temperature. And apologies. And when we walk in, the temperature in the cabin is 3 degrees, okay? 3 degrees is cold, so we decide to crank up the heater. How many times have you done this before? Perfect. So we crank up the heater, what's gonna happen? In time, the temperature inside the room is gonna go up, right? How's it gonna go up? So basically that's, it's one of the examples we actually did last week. It was the heating example, it was a first order system, right? So how is it gonna go up? Well, we start from a if the temperature is already 3 degrees and you crank up the heater, definitely the temperature is not gonna go down. Maybe the definitely is maybe, for this specific case, it's not gonna go down. There is a special class of systems for which these kind of tricky things happen, but we'll study them later on. So temperature is gonna go up. How is it gonna go up? Is it just gonna go up forever? Like until the house melts down? No, right? So there's gonna be kind of something that's gonna go up at the beginning and eventually it's gonna converge to some value, right? What is this value? Well, we don't know, we'll figure it out. This is y at, let's say, at steady state. I'll write it as y of infinite time. Please don't ever, I never wrote this, okay? So, okay, fantastic. How do we figure that out? Now, let's suppose that this problem, this model, is described by these equations. Okay, so the x dot equals ax plus bu and y equals cx is represented by this very simple scalar first order system. So x is just one variable. U and y are as defined. So this basically means that a is equal to -2, c is equal to 6, b is equal to 1, which is what is multiplied here, basically. And then we have d equal to 0. Okay? So, fantastic. Now, how are we going to go about to figure out what's the solution of these equations? Well, we leverage the concept of linearity that we defined in the first class. And what's linearity? Linearity is about superposition principles. So if you break down the input signal in two different things, then the output is going to be the sum of the outputs of those two individual inputs, right? So how are we going to do this? So we are going to choose a situation where u is a function of something that depends on the past and something that depends on the future, right? So if you followed a little bit the dots that we placed in the last 2 hours of class, so what is the thing we introduced that represents the past, right? That we introduced it on purpose because we don't really want to remember the whole past. It was these state variables, right? So what is a signal that what is the state variable that keeps in mind everything that happened up to some time t that we consider the beginning of what's interesting to us. So we'll consider the first signal you passed. That's something that was only affected by an input in the past up to some time t0. So x of t0 is, or otherwise means x evaluated at t0, we'll call it x0, and it's the initial condition of the system. And then we'll consider another signal instead that is what's going on in the future, right? So something that is actually affected by the input variable u of t. So basically, the output then is going to be, the output of the whole system is going to be the sum of two different outputs. We'll call it, just for, let's say, y past, so to speak, plus y future, although we'll have proper names for these two and we'll introduce them soon. This is only a function of the initial condition, and this is only a function of, is a function even of the input and some other stuff. So basically, we break down these two components such that it's as if we're poking our system with a signal that is whatever it is up to time 0 and then goes to 0, and the other one that is 0 up to time 0 and then goes to 5, okay? We're just study what's the output of a system to these two different input signals. Why? Because they're meaningful. Why are they meaningful? Because we can imagine it. We want to divide, basically, what is the effect? And when I say the effect, I mean the dynamic of the system, how the output changes as a result of a direct stimulation as an input signal coming in with respect to what is the output of a system because of its initial conditions, okay? Recall always the example of the pendulum. If I have a pendulum, I'm keeping it from above, it's stable, like this, okay? By the way, x is 0, 0, and u equals 0 was exactly this stability point, okay? The first term, which here we call the one that depends on the initial condition, what is it? It's the dynamic. What happens if I put this pendulum here? So I choose an initial condition that is theta different from 0, it's whatever, it's 30 degrees here. If I leave it, it will have its own dynamics when I start oscillating back and forth. That's a dynamic induced only by changing the initial conditions. I'm not applying any input to it, right? So we call this initial condition response, okay? Or sometimes referred to as the free dynamics, or the free response. So basically, it's the y that depends only on the initial condition. And there's the other part that instead depends on the actual input. Say I am actually pushing this guy around, I'm poking it, I'm shooting a bullet at it, I'm actually applying an input, a physical input on the system, then of course the dynamics is going to be different. We'll call that second part the forced response. So, okay, the whole idea here is just to say that since we define the two signals in such a way that in the initial condition part, x naught is equal to the initial conditions, but the x naught of the forced part is equal to 0. So this basically is 0. And here this is equal to 0. Clearly the sum of these two signals is like the sum of two input signals going to the system. So we can sum up the outputs. How do we, so now what's the problem? The problem now is figuring out these two terms, right? So what is the response of a system if you just change the initial conditions but keep the input equal to 0? Problem number one. And problem number two is, what is the output of the system when you pretend the initial conditions are 0 but you apply some input? So let's just start from an easy case. The easiest case is where the A, B, C, D matrices of the linear time invariant formulation are actually scalars, okay, just numbers, 1, 2, 3, 4, but just one number, no matrices. And x naught is equal to x0. So these are the initial conditions, okay? Here we want to find the homogeneous responses. Homogeneous means that there is no u of t, okay? Homogeneous means u of t is equal to 0 at every time instant. So how do we solve this? You should know from your math classes that the solution to this first order differential equation comes in the form of E at the AT times the initial conditions. Is this obscure to you, or how many have heard of maybe something similar in there? Okay. Good enough. So, well, we can later on see, try to convince ourselves that this is actually the case, but we will not derive it. So, x of t is equal to e at the AT times x naught, where x naught is the initial condition, and here we're supposing that the inputs are equal to 0. We call this function here, which is very characteristic, a state transition function. Note that this depends only on time and on the variable a, which is what is multiplied here by the x. So, well, if we know that x of t is equal to this, then what is y of t? Well, y of t is simply c times x of t, right? So we will get y of t is equal to c times the state transition function times x naught. So what is it in this case of the cabin? Well, here we're saying that the initial conditions in this case is equal to 3, and we have no input. We're just studying the free response. So how will the temperature in the room change based on this? Well, if there is no inputs, or we're pretending that we have u equal to 0 here, we just have these initial conditions, what's going to happen is that the temperature will start going down, right? And it will asymptotically go to the external temperature that we said was equal to 0, okay? And this is the first part of the response, was what we call the yc of t. Now the question is, okay, how do we go about instead and find what the forced response is? Well, if to look at the forced response, we need to just do a few passages. So, do we have the time to do them? Yes. So, now we imagine the initial conditions to be equal to 0, okay? And we only care about having an input signal, u of t, that is bigger than 0 after some time. So how are we going to do this? Well, should I use the blackboard or should I write here? By consensus, who wants me to write on the thing? Who wants to use the blackboard? Blackboard, done. Okay, so now you're going to use the blackboard. So, what's the problem? We have x dot, is it big enough? Can you all read? Maybe? Yes. X dot of t is equal to ax of t plus b u of t. And for now, let's keep it at this. So actually, in this case, we're saying a is just a number and b is just a scalar, okay? So what are we going to do? The first thing we're going to do is multiply both sides of the equation by e at the minus a tau. X dot of t. So we can do this, right? It's a legal move. It's like I'm just multiplying left and right of an equation by some term that is the same. So e at the minus a tau times what? Times ax of t plus b u of t. Okay? Can you see? Say it again. This is x dot. It's dirty. Blackboard doesn't help. Okay. So, okay, how does this help? It helps that if now we can say, let's integrate both sides of the equation from some time 0 to some time t. Keep in mind that here we are implicitly assuming that t naught, which is the initial condition, the initial time, is equal to 0. Otherwise, we could just put t naught here and everything would be fundamentally the same thing, just a little bit more complicated. Okay, so what's up now that we have these two parts of the equations? How are we going to deal with them? Well, some of you, of course, here, but to be proper, we should, this becomes tau, this becomes tau, this becomes tau. Here we need a d tau, and here we need a d tau as well, just not to confuse the variables. So what some of you might recognize this as something we can deal with. It's we can integrate by parts. So just as a reminder, if you have the integral of some function that you can consider as derived times a function that is not derived. This can always be written, let's say, between A and B as the fg evaluated at extremes minus fg prime in D, whatever it is. I've not put it, okay? So in this case, of course, we consider this as the derived function. So we can write the left side of the equation as what? We can write it as this non-derived, so it would be just x without the dot of tau times what? Times g not just as it is, e at the minus a tau, evaluated between t and 0, minus what? Minus the integral from 0 to t. Of what? Of this not derived, x of tau, times the derivative of the other function. The derivative of an exponential, it's an exponential itself, times this part here, minus a. So minus times minus becomes a plus, and the a, we'll just put it here. The other side of the equation doesn't change at this point, but I'll just break it up to make it a little bit more clear. So e at the minus a tau, let's put the a here, x of tau in d tau plus the integral from 0 to tau of what? Of, how shall we write this? Let's write it like this. B e at the minus a tau in times u of tau in d tau. So you will notice that this term here and this term here are exactly the same, so they can go away. What we're left with is those other two terms, which we can, so this thing here, what does it mean? It means this thing evaluated at t minus the same thing evaluated at the second part. So what we get is x of t times e at the minus a t. Shima, double check my math if I'm doing things wrong. Yeah. Minus x of 0 times, x of 0 e at the minus a times 0, right? So this is equal to 1. This is by definition our x naught, which is our initial condition. Since we're studying the forced response here, so it's a problem such that the initial condition is equal to 0. In this case, this is equal to 0, so we can remove this part. And on the other side, what we have left is just the integral from 0 to time of b e minus a tau u of tau in d tau. Now, what we really care about is x of t. Now, we're doing all of this to find the solution x of t equals, then once we have x of t, it's easy to find the y of t. Well, we can multiply now both sides of the equation by the inverse of this second term. So we finally get x of t is equal to e at the at, the inverse. Note that here this integral is in tau. So t is a constant with respect to the integration variable and can be brought inside the integral. So 0 to t of b e at, so it's e at the plus a t. So minus a tau minus t, or let's just write it t minus tau, which is how you'll find it on your textbooks, times u of tau in d tau. Okay, boom. So this is the very important second part of the solution, okay? And we will not give this a special name, but so we know that y of t is equal to what? Y of t is equal to c times x plus d times u, right? So here, apologies for the confusion, but this is not d as in the integral, it's d as a whatever number d, a scalar matrix d. So where am I heading here? I'm heading to the point that the actual output in this case is the forced output, the forced response of the system, because we're considering the initial conditions to be 0 and the input to be whatever, is a c times this. So it's integral from 0 to t of CBE at the AT minus tau times U of tau in d tau plus d U of t. In most practical situation, you'll always see this d equal to 0, so this term won't appear. But keep in mind that this is the actual solution. There is that extra term there, okay? Now, this term here should look kind of familiar, maybe, to those of you who like math, maybe. But it's not necessary to get into details now, but it will come, it will have many, many fun properties, okay? See you in 10 minutes. Okay, so was this clear, more or less? I guess if it was less clear, you would have come and asked questions. So those who did not, do you have any comment, question, or doubt right now before we proceed? No. Okay, so what's the bottom line of all of this? The bottom line is that we now have an expression for how the state evolves in the presence of an input signal that is different from 0, but 0 initial conditions. Note. So we got this term here, right? Before we said for the initial, for the free response solution, we had y of t. Let's say this was the initial condition part from the previous slide. We got c e at the at x naught, right? And we called this the state transition function. Well, here it's the same thing. This is phi of t minus tau, okay? It's always the same transition. So this is just to give you an intuition that there's something going on. Like regardless how you poke your system, there's some fundamental structure in the response, okay? And we will give this fundamental structure a name later on. Okay, so back to the cabin. What's going on? Well, now we're just pretending that the initial conditions are 0, right? Because we're studying just a component of this force solution. So suppose we start from 0 initial conditions, but now we've got an input that is different from 0. The input is 5, okay? So what's going on? What would you expect as a solution? Well, here you can actually calculate it. Before we said it in a wishy-washy way. We said, sure, the cabin will not melt, so eventually it's going to go up, but it's going to stop somewhere. But now we know exactly where it's going to stop, right? Because if I'm not mistaken from our model, which I should have copied back here, what was it? Like 2 minus 2x plus the 6u and y equals to what? 2x? Was it x? Yes, 1x, okay. So what's going on? Well, now we know that y of t is equal to that stuff there, right? Which is the integral from 0 to t of c times b times e at the at minus tau times the input, right? So, well, this is u of tau. Do not mistake the t's and the taus here because they're two different things in d tau. So in the interest of time, I will not go through these calculations which are expressed here in these passages, but the idea is like u of t, you know what it is, it's 6. No, in this case we said it's 5, right? We're putting our input constant at 5. 5 for every time instant. So it's a constant, take it, slam it out of the integral. C and b, we know what they are. C is equal to 1 and b is equal to 6. Right, so c times b times 5 is equal to 30. You bring it out. Then it's the integral from 0 to t of whatever of this exponential term. Just do a substitution of variables to solve the integral. Now you actually have a proper solution. So this means that if we put 15 up here, the forced response is going to go from 0 up to here. Okay. Now here there is something worth mentioning. So is it like I drew it? Or is it maybe like this? Or is it maybe like this? Or is it maybe anything in the middle? So how do we actually know how fast that does the system respond to this input, the step input, okay? What's a step input? A step input is basically an input that is 0 up to time 0, and then it starts that is at is some constant value throughout. Okay, so we can introduce a parameter. I'll just redo the drawing because I messed up the main one. So say this is the steady state value, and this is the solution we have. We introduce this concept of time constant, which is a measure of how quickly the system responds. A first order system responds to a step input. And you just take the derivative of the y of t, this is a y of t, at the origin, and you get this. And basically, where it intersects the steady state value here, this is called tau. And tau is you can easily find the solution to be -1/a, where a is -2 in this case, is the a of the ax. It's a measure of how quickly the system responds. Having a smaller time constant means that the time the system takes to, I don't want to get too much into detail of this, but the idea is that you can show that by doing this game, what you're measuring is how long does it take the output of the system to get to like 63% of the steady state value, roughly. And yeah, so having a smaller time constant means this situation here, which would mean the system responds more quickly, okay? Having a bigger time constant would mean that the system actually reaches this value up here, so it responds more slowly. Later on, this is going to be something that we can use to specify how you want your system to behave. Now, say you have a first order system, and as an engineer, you say, no, I want it to be performant, right? What does it mean? It has to get to the point I want it to be in 1 second, in half a second, and this tau, the time constant, is a way to express this performance, the speed that the system takes to get where it needs to go. And we'll see that it even has relationships with the bandwidth of the signal, which is a concept we'll talk about later on. So putting things together, what did we do? We looked at the various components of the solution, and we can now finally tell what is how does a linear time invariant system evolve. So given x dot equals ax plus bu, and y equals cx plus du, the general solution, and given an initial condition, so what is known is u of t is known, y can be measured, but this is a different point, sorry, and the initial conditioning. The initial conditions need to be known. Then the state variables will evolve in this way here. As we saw before, this is a component that depends only on the initial condition. It does not depend on the input. Notice there's no u of t in that first part. And then there's this other piece here that conversely depends only on the input. It does not depend on the initial condition, and we called this the forced part. The y, so the actual output, is just cx plus du, which means that you multiply this x by c, and you've got c e at the end. So just c multiplied by all that, by the big equation above, plus the u of t at the end. Okay, so it's not surprising that it's, of course, the output, a linear combination of different inputs. It's a linear system. And fundamentally, it depends on the initial condition and the input. That's what's the takeaway. This is the absolute general solution of a linear time invariant system, with the only particular case, actually, that we pretended that A, B, C, and D were not matrices, but were scalars. We just called them A, B, C, D, now to make our life easy. How much does this change when we consider the actual matrix case, right? So first, let's look at the different components. So now we've got a part that depends on the initial conditions, which is this one, the one that we drew before to be like this. In that case, this would have been the time constant of the initial condition part. And then we had the second component instead that started from 0, initial condition, and went up to 15. So now what's the actual output of the system? Well, the actual output of the system is the sum of the two. So it means that at every time instant, we need to sum up the two components. So at the beginning, this is 0. So we start from here. And where do we go? Well, eventually this goes to 0. So it's only the other signal. So basically, it's going to be something like this. Okay, the green part is the actual y of t. Make sense? Not really? Yeah, maybe? Speak up. Good enough? Okay, fair. Okay, so very well. This is nice, maybe even interesting, but it's not exactly what we wanted to solve. We wanted to solve the matrix case. So how does it change with the matrix case? Well, it doesn't change much. The bottom line is that everything is the same. But we need to keep in mind some details, because details are important. This is like a parenthesis. So what is the details? So if you remember, we used, we derived the solution here, right? And really, the only property that we used that was relevant, where A was involved, was this one. So at this passage here, we said, the derivative of an exponential is whatever, right? And we use that to do the integral by parts and so on. So what if we have, so with this, we knew that the derivative of this was, what was it? E at the AT, right? But what if we have E at the AT, where A is a matrix, right? That's might not be obvious. Like, so how does it work? What is it? How do we define a matrix exponential, right? So let's keep in mind that the Taylor expansion of an exponential can be written in this way. You all know what, are you familiar with Taylor expansions? Raise your hand if you're familiar with a Taylor expansion. Why are you not all raising your hands? Is it you are? So I hope you're familiar with Taylor expansions. If not, maybe we can cover them explicitly in the exercise sessions, just to make sure, because remember, Taylor saves your life, okay, in control systems, I mean. When you're dealing in your professional life with a system that is a mess, or in general, when you have a nonlinear situation that it's going to be complicated because all real things are nonlinear, the first thing you do is always tailor it, okay, and see what happens. That always gives you an insight on a first cut insight on the situation. So, say again? Of course, but you need to use the box. So let's see if this is on.
So from last year, from linear algebra 2, we know how to calculate e to the power of a matrix with the eigenvalues and so on. So why don't we use that and use Taylor polynomials?
You mean this?
Maybe. No, yeah. Not that. No, we didn't use any Taylor at all.
We're not using Taylor, but we're saying let's define the matrix exponential such that it has the same Taylor expansion, such that it has the same derivative property. As long as it has the derivative property, the other thing is going to be satisfied as well. And this means that all the passages we did for the scalar case are exactly the same for the matrix case. Does it answer your question?
No, not really, but let's see where this is going.
Okay, fair enough. Okay, so the idea is let's define a matrix exponential such that it satisfies the same integrability property so that we can redo all the passages. And this means that through this definition here, the Taylor expansion is very similar. Of course, similar because you don't have a 1, you've got an identity matrix. And I guess you all know what the power of a matrix is, right? You say the A matrix is square. What does it mean? It's nothing but A matrix times A matrix, okay? So that's nothing special. So by just keeping in mind this thing, and I promise to you that this is one of those details that 80% of you will get wrong at some point in their lives and spend a week to figure it out or get a bad grade in an exam or both. So like matrix exponentials are different from regular exponentials, okay? You have to calculate them in a different way. But if you keep in mind this is a small property, well, then everything is the same. The general, the free response has the same form as the one we studied before for the scalar case. And the forced response has exactly the same form. Of course, now what we have to keep in mind is that we have to plug in the different matrices in place of the scalars that we had before. So this is actually the general solution to an LTI system, okay? It doesn't get more complicated than this. Now we know how a system, a linear time invariant system, which is the systems we care about in this course, how it responds given any input, any initial condition. If you have a model of the system, which means you know what A, B, C, and D are. Okay? So keep in mind that A times B, I would say, the product of matrix do not commute. Okay, so let's take two matrices M and N, of compatible dimensions such that we can actually do a multiplication. In general, this is not true. Okay, so it's not really going to be a big deal in our course, but keep in mind that when you're dealing with matrices, the order is important, so keep track of where things come from. Okay, so how do you actually compute this? Now, we kind of made a big step by just saying, hey, just make this property hold and never get it wrong. But what does it mean not to get it wrong? So how do you compute it? How do you actually do it? Well, either you calculate a lot of terms of the Taylor expansion until you get tired or the terms are, are negligible, or you just use a computer to do it, and that's what you will always do in your life. The secret is that nobody ever computes one of these things by hand, okay? So don't worry about computing it, but when you write it in your programs to implement controllers, keep in mind that there is a dedicated function for matrix exponentials and you don't have to use the traditional ETH because it's a different thing. But one thing that is relevant to us is that if the A matrix, so if the matrix at the exponent has a specific structure, that is, it's upper triangular or diagonal, then we can rewrite the matrix exponential in an easier way. So we will not go into how this happens, but just take at face value that if you have E at the AT, where A is a diagonal matrix, then this is equal E at the lambda 1t, E at the lambda 2t, 0, 0. Where lambda 1 and the other case is, you can read it here. What are lambda 1 and lambda 2? Lambda 1 and lambda 2 are the eigenvalues of the A matrix, okay? So the eigenvalue, everybody knows what an eigenvalue is, right? Eigenvalues, eigenvectors, like bread and butter, correct? Hands up. Yes. That region of the room, no. It's like, did they skip to the math course or something? Okay. Anyways, go check your eigenvalues and eigenvectors. Otherwise, you're in big trouble. Maybe we're gonna cover these things again in the exercise sessions just to make sure. So why are we making? So why is this core class taking this direction? So it seems like I'm arbitrarily bringing up these things. We're going to see in next class that basically any system of the world, anything we can write x dot equals ax plus bu, can be rewritten either in the first or the second form. So we can always, through an appropriate math trick, diagonalize a system or express it in a Jordan form depending on what the properties of the system are. So basically, if we understand these two cases, we understood everything there is to understand by just adding a preliminary step that we'll talk about next time. And the physical interpretation is really interesting as well, but we will get to that later. Now let's just focus on what can we gain from expressing the matrix exponentials in this way, and why are they relevant? So they're relevant because they allow us now to write out the outputs of a system in a more readable way. So no longer with these weird math expressions, but C E at the AT x naught which is the free response, can be very easily, can be expressly written as a C1 set. Suppose here we have X that is a second order system, so it's a 2 by 1, and so C as a consequence, the C vector must be 1 by 2. So we can literally write out these things, then we can patiently do row by column, and do everything, and what we get is the sum of these two terms. Now, remember, these lambda 1 and lambda 2 are eigenvalues of A, okay? So what are these two terms? Well, they are two exponential terms that are weighted with the output matrix, the C and the initial conditions. So the part of the free response of the cabin we wrote before, and that was a first order system, so it was just one term, but any nth order system can be rewritten, this part of the output can be rewritten as a sum of exponential terms, okay? This in the case that the matrix A is diagonalizable, okay? Now, suppose instead that the eigenvalues are not real numbers, but they are imaginary numbers. You know, when you calculate the eigenvalues of a matrix, of a real matrix, you could get, suppose you get complex conjugate, so complex eigenvalues, and they're always going to be complex conjugate, they're always going to come in pairs. We can do exactly the same thing as we did before, but we recall now, so that's basically exactly the same thing as before, just with a few extra passages here that are nothing worth mentioning, but we will do it regardless. So the idea is, here you always do C1, C2 times E at sigma plus J omega, and E at the sigma minus J omega 0, 0. And here we've got x is 0, 1, oops, x 0, 1, and x is 0, 2. So this is this part here just rewritten. Now what are sigma, j, and omega? Here we're saying basically that lambda 1 is sigma plus j omega, and lambda 2 is sigma minus j omega. They are both eigenvalues of the A matrix, and they're complex conjugates. So sigma is what? Sigma is the real part of lambda 1 or 2, and j omega is the imaginary part of lambda, and j is the imaginary particle, it's the root of -1. Okay, so if we write this down, then we get we recall that E at A plus B in general is equal to E at the A times E at the B, which is the property we use here. Now we separated the contribution of the real part of the eigenvalues from the imaginary parts of the eigenvalue. So sorry for the parenthesis. Like, this might seem a little bit boring, but it's kind of one of the three most important concepts of the course, so to speak. Like, once you get this, you'll be able to tell a system when is it stable and why, and it's totally understood, and that kind of takes care of 25% of the reasons why control systems exist. Okay, so it's worth 10 minutes. And, so the idea is we separate the real part, the contribution of the real part from the imaginary part. The real part, you just put it here. You can just rewrite this in a way that you have a weight times the real part times something that depends only on the imaginary part. Okay, if you crank out the calculation, this turns out to be, you can relate alpha to alpha 1 and alpha 2. If I'm not mistaken, this is the inverse tangent of alpha 2 over alpha 1. So, and you get to this last passage by using Euler identity. This is a very powerful equation, and some say it's one of the most beautiful equations there is. So the point here is that if we've got, the point here is that the eigenvalues of the A matrix determine what kind of response the system will have. And if they're real, you get just a sum of nice exponentials, okay? If these terms, these eigenvalues are complex, then we get something a little bit more messy, but it's not that much more messy. It just has always the exponential part like before, times a sign. So there's an oscillation on top of this exponential part, okay? So this is how it actually looks. Basically, we said that y of t is equal to some value times e at the sigma t times the sine of omega t plus phi, okay? Where this omega is related to the imaginary part of the eigenvalue. This sigma is related to the real part of the eigenvalue. So basically, the response is something that always decays as an exponential. So this is basically the envelope of this response is given by alpha e at the at. And then there's the sine wave, this oscillatory behavior in the middle. And it's possible to, so the oscillations, of course, are related to the frequency omega, to the imaginary part of the eigenvalues. If we were to just calculate the forced response, so if we give a step input to the system that has eigenvalues of this kind, what you would see is that the solution, the output starts going up, and it oscillates, and eventually this oscillation dies off, if we're lucky, and we get a behavior of this kind. So what instead, so these two cases were real eigenvalues and distinct, complex eigenvalues, complex conjugates. Now there's another case, which is what if you have real eigenvalues, but they're not distinct, they're repeated, okay? That's when the diagonalization fails and we have to have, we get these Jordan form representations, these upper diagonal terms. So what is interesting here? What is interesting is this part. So basically, we get the same structure as before. Now, lambda is a repeated eigenvalue, so it's the same. There's no lambda 1 and lambda 2 are the same. But we get this t term, this polynomial term. So this means that if we just crank out the calculations, recall that this is like this is x01, x02. Now we get the same two terms as before, so a weighted sum of exponential terms, but now we have this new addition here, and it isn't too much of a big deal in general. But look at this case. Now suppose lambda is equal to 0. Okay. So what happens? It happens that all the exponential terms go to 1 because e at 0 something is equal to 1. So say C1 and C2 are just normal finite terms, and so are the initial conditions. Now the solution is equal to C1 x01 plus C2 x02, which are constants. This is just a k, but we have a term as a function of time. Okay, so if you have, just keep this thing in mind, eigenvalues at 0 and they're repeated, there's a polynomial term coming out in the output, which means that if time goes by, if t grows, then the output grows as well. What is an example of this? An example of this is m equals fa. We can rewrite any ordinary differential equation in this state space form that we've learned. We just introduce x1 equal to p, similarly to how we did, this is a second order system, similarly to how we did with the pendulum before. X2 is going to be equal to x1 dot is going to be equal to p. So if we rewrite the equations, we can put it in the form ax plus bu, as we did before. Here the u is the input, right? In F equals ma, the input is the external forces that you apply. This is equal to u. Now you can see that the A matrix has two eigenvalues in 0, right? You can tell directly by inspection here. So this means that the output is going to be a polynomial, and this is not surprising. But this just to say that these situations happen pretty often in real systems. So So let's just summarize these three different cases. And basically, any matrix can always be reduced to one of these two cases that we saw, either diagonal or joiner form, through a process that's called diagonalization, or we'll call it modal decomposition next class. If you've got complex eigenvalues, they'll come in complex conjugate pairs. And the output of the system is going to be a combination of different terms. In the simplest case, when you have distinct and real eigenvalues, it's going to be just the sum of a bunch of exponentials. If you have complex eigenvalues, so in this case, you'll just have term 1, term 2, and then they'll just sum up like this. If you have complex conjugate eigenvalues, you're going to have, if the system is, let's say, if something happens, it's going to be something like this. So there's going to be always this exponential behavior, but with a superimposed oscillation. If you have repeated eigenvalues, then you have these polynomial terms creeping in, which in general are not a problem, where a problem is defined as something undesirable, but we'll introduce it soon. So if, just recall, just keep in mind that if the eigenvalues are equal to 0, then you have an unbounded output. So if time grows, then the output has a polynomial form, so it will grow polynomially. This is how the output of a linear time invariant system will be, and other contributions will come just from the du term, so the input. Okay, so finally, now we know how to mathematically express the output of a system. How is this useful to us? Now we have to start talking about what is it that we like, what is it that we don't like, what is it that is desirable, what is it that it's not desirable. So we introduced this concept of stability. So that's a very important idea because it's the first objective of a controller. What is a stable system? So there's different kinds of stability. In this, we can imagine them fundamentally as two big families. Just remember this thing. I stress it because it's maybe not obvious. So in control system, the whole universe is a bunch of blocks, okay, which we call systems. The systems receive an input and give an output, okay? The input, you get to decide what it is in general, okay? Plus minus some perturbations that might overlap on it. The output, you get to measure it, okay? But we've just seen that this is a machine. This is a mathematical machine that gets numbers as input and spits out numbers as output. But it has an internal dynamics. Things change, things go on under the hood. We don't know exactly what's going on under the hood. We know that we can express it by at least for the class of systems that are interesting to us, we can express it like this. Okay? So my bottom line is that this machinery has a dynamics x dot going on. There is this bunch of variables, the state variables, that are have their own behavior, change, okay, vary in time. And the way they vary in time is not necessarily captured by the output, okay, because the output is a combination of these state variables. So we will talk about two different kinds of stability. One is an input-output stability. So all we care about is if the output of the system is going to be stable, which is something we're going to introduce now. It doesn't blow up, okay? And then there's the other kind of stability that is, we can think about it as an internal stability. So it's an input to state stability. So do the state variables blow up? Sometimes the state variables might blow up, but the output, you might not see that in the output. We'll see that this is something that will happen later on, and it's something we need to take care of. So let's go with our definitions. We introduce the Lyapunov stability as something in the following form. So suppose we have a system that has, for every bounded possible initial conditions, and zero input. So take the system, leave it at some point. then the dynamics are going to just evolve in some bounded way, okay? So this is the concept of internal stability, if you want. You get for every possible initial condition that is bounded. What is this? This is a norm, okay? This operator here, you can think about it as a measure of some property of the signal U. I'm not going to get into details of this now. Imagine it as the 2 norm if you want. So it's just the Euclidean length plus the sum of the squares of the components. So it could be x0, 1 square plus x0, 2 square plus blah, 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 x0 and square. So if this is a not infinite number, then the states of the system are going to be bounded, okay? It means they don't go to infinity. If a system satisfies this property, we're going to call it Lyapunov stable. Let's think about it physically. What's going, it's like always the pendulum thing before, no? So no inputs involved here, only initial conditions, okay? So if I put any initial condition that is bounded, means it doesn't go to infinity. So what are the states here? The states here, if you remember the example, are position, and angular velocity, okay? So here it's difficult for me to show you an example where an initial condition on the angular velocity is different from 0, because I should let this go with a push, basically. But if I let it go and the dynamics, that is the state dynamics, x of t, is bounded, that is remains within some closed, let's say, neighborhood, we call it Lyapunov stable. In particular, we call it asymptotically stable if this ball is exactly 0. So an example of the first case would be, imagine you take a pendulum and you bring it in an ideal world where there is no friction, okay? So if you just let it go, and there's no friction, and the cable is massless, and there's no friction at the hook, and there's no friction of the air, the thing will continue going forever back and forth, okay? That's a stable situation because the state variables, the position and the angular velocity, just trade each other off, but they always stay bounded within some contained region, right? An asymptotically stable example would be, well, always the pendulum. I can let it go at any finite, of course, initial position. If I just hit this with infinite energy, like I shoot it, of course, it's not going to be stable. It's going to blow up, okay? But that doesn't count as a stability property. If a pendulum in the real world, where there is friction, if we let it go at any position, it will do its oscillations, but eventually it will just go back to 0, right? It will eventually just stop because there is this dissipation going on. That's the example of asymptotic stability. That is, for every possible initial condition that is not infinite, we can just let it go, and eventually, when time goes to infinity at steady state, the state variables will just converge to 0, exactly 0. Okay, it'll go back to an equilibrium point. And then there's the concept of external stability, which is, if you want, the most intuitive. If you want to remember just one thing from this slide, just remember this. A system is stable when it's BIBO stable, when it's bounded input, bounded output. If you give finite energy to a system, the output will have finite energy. Which is intuitive, right? If you don't, so if we send an input signal to a system that is not infinite, then the output will not just grow on its own. If that happens, the system is unstable. If the output of a system remains bounded, then we call it input-output stable. Okay, so what is instability? Just to re-say it, well, we have to worry about things that grow in time and to become unbounded, okay? So remember the case of the lambda equal, if we had eigenvalues that were real but repeated, then we had that polynomial terms coming out in the output. Well, if you have a polynomial term and the lambda is equal to 0, as time goes by, y of t just grows polynomially. And if it grows, it's not bounded. If it's not bounded, the system is unstable. When you have a system, you're controlling a system with eigenvalues, with repeated eigenvalues in zeros, be careful because it's an unstable system. So how can we tell if a system is stable or not just by looking at it? So it's just putting together now the outputs that we saw before, expressions as a function of the different eigenvalues. If you have real and distinct eigenvalues, then we saw the output was a sum of these exponential terms. Like, focus a second on these exponential terms. When is an exponential term bounded versus unbounded? It has a lambda at the exponent. So if lambda I is a negative number, that's e at the minus of something t. If t goes to infinity, e at the minus something t goes to 0, right? Boom. So that's good, because we know the outputs are sums of the e at the minus something. So if all these terms goes to 0, means the output goes to 0. A system that is characterized by the eigenvalues of the A matrix that are negative numbers, it's asymptotically stable. If are negative or equal to 0, then they're still stable. If you plug lambda I equal to 0 here, you will see you get e at the 0t, which is 1. It's basically a constant. It's not the ideal situation, but still bounded, right? A constant doesn't grow in time, it stays constant. It's a constant. And the same goes here. So even if you have complex conjugate eigenvalues, well, what determined how the system, if the system was bounded or unbounded in time, really depended on that real part here. Now, if you look at a few slides ago, we said that was the envelope of the response. And of course, the thing that they're imaginary introduces these nasty oscillations, but doesn't matter if it oscillates as long as the oscillations die off. This is the pendulum. It oscillates, but eventually it dies off, right? So, and sigma was the real part of the eigenvalues. So again, it's the same conclusion in both cases. System is stable when the A matrix has negative eigenvalues. Asymptotically stable. The real part of the eigenvalues is negative. And if it's equal to 0 instead, you get still stability. Now, if you have repeated eigenvalues, then, and you have them in 0, which is a very particular case, then these would go to 1. This would go to 1, and you would get these exponential terms, these polynomial terms that just make your output become unbounded. So, when is a system stable? In a nutshell, it's just need to look at the eigenvalues of the A matrix. It's really nice. And you just need to look at what the real parts are. If the real parts are negative, we're good. Asymptotic stability. They're equal to 0, still stable. If they're bigger than 0, the system is unstable. It will grow in time. The only asterisk we have to keep in mind, if they are 0 and they're repeated, then we've got an issue. So today we actually finished the class, which is interesting. We did all these things here, so are there any questions, comments, or doubts? Beautiful.